Welcome to Techno Sapiens.
Shall we? Today we're going to demystify the invisible mechanical magic that is quite literally powering our entire modern world. We interact with electricity every single day, but we rarely stop to think about the incredible journey it takes to actually get to us, or the honestly ingenious engineering that makes that whole journey possible. I want you to picture a glowing city grid at night. You've got these massive, high-voltage transmission lines buzzing overhead, carrying hundreds of thousands of volts of electricity across vast distances. Now, contrast that monumental power with, well, the tiny little phone charger you plug into the wall next to your bed every night. That charger only needs a few volts to safely power up your device. So the big question is, how do we bridge that massive gap? How do we tame that absolute beast of an energy surge into a safe, usable trickle without blowing out every single appliance we own? Part 1. The voltage mystery, a machine with no moving parts. So when you think about a machine, you usually expect gears, pistons, maybe some spinning rotors. But with a transformer, there are absolutely no electrical wires connecting the two sides. None. Zero. Instead, it's just magnetism transferring the energy. It's literally an invisible magnetic force doing all of the heavy lifting here. It's just such an incredibly elegant application of pure physics. Our entire electrical infrastructure completely relies on this exact principle, performing a monumental task while sitting entirely still. Part 2. How a transformer works. Inside the iron core. If we were to crack one of these things open, we'd find this beautifully simple setup. On one side, you've got the primary coil. This is wrapped around a central iron core, and it acts as the entry point. It receives the alternating current, the AC electricity coming in. On the exact opposite side, separated by that iron core, is the secondary coil. This is the exit point, and its entire job is to deliver the brand new modified voltage out into the world. Okay, so how does the actual physics work here? It basically happens in 3 super simple steps. First off, alternating current flows straight into that primary coil, and because it's an alternating current, it pulses. Step 2, this pulsing creates a changing magnetic field that travels right through the iron core, holding those 2 coils together. And finally, step 3, as that fluctuating magnetic field passes through the iron core, it washes over the secondary coil and literally induces a new voltage right inside it. No touching, no wires crossing, just the invisible bridge of a magnetic field. Part 3, step up versus step down, controlling the voltage. So how exactly do engineers control this induction to manipulate the voltage? You might think you need a complex computer chip for this, but nope. You literally just change the number of times the wire is wrapped around the core. If you want a step-up transformer, where the voltage increases, you simply make sure the secondary coil has more turns of wire than the primary coil. On the flip side, if you need a step-down transformer to decrease the voltage, you just use fewer turns on that secondary coil. The ratio of the wraps completely dictates the final voltage. It is elegantly, brilliantly simple. Let's bring this back to everyday life for a second. Step-up transformers, the ones with those heavily wrapped secondary coils, they're mostly used right at the power stations. By jacking the voltage up incredibly high, the electricity can actually travel cross-country over long distances with maximum efficiency. But obviously, you don't want cross-country voltage bursting out of your living room wall. So step-down transformers are used right before the electricity enters your neighborhood, and they're even miniaturized inside your phone chargers, your TVs, and your laptops to keep everything totally safe and functional. Part 4. The real-life power grid, a micro to macro journey. The really crucial point to grasp here is the sheer scale of the energy we're dealing with. Let's start right at the source, the power plant. Electricity typically leaves a generation plant at around 20,000 volts. That is a massive amount of raw power being generated right out of the gate. Now contrast that massive 20,000 volt starting point with our final end point, just 230 volts. That's the safe, highly reduced voltage that a final step-down transformer actually lets into your home for everyday use. Getting from 20,000 all the way down to 230, well, that's where this entire system really works its magic. Let's actually map this physical journey out, right from generation all the way to your living room. We start at point 1, the power plant, generating those 20,000 volts. Then boom, immediately at point 2, a step-up transformer hits the current, jacking it up to hundreds of thousands of volts. Why? So it can survive point 3, those massive transmission lines that carry power efficiently over mountains and across state lines. Once it reaches your city at point 4, it hits a substation, where a step-down transformer heavily reduces that massive voltage. And finally, by the time it reaches point 5, your home, smaller step-down transformers have reduced it all the way down to that perfectly safe 230 volts, ready to brew your morning coffee or charge your phone. When you step back and look at this whole journey, it becomes pretty clear. Without these devices, modern electricity distribution would be horribly inefficient and just incredibly expensive. Transformers are absolutely the unsung heroes of our modern infrastructure. Without the ability to dynamically step up voltage for travel and then step it right back down for safe use, we simply couldn't have a functional, affordable grid. It just wouldn't work. It really kind of makes you pause and look at your surroundings a bit differently, doesn't it? I mean, can you even imagine modern life without this silent, motionless, magnetic machine just working tirelessly behind the scenes? Every single time you flip a light switch, you are relying on an invisible magnetic field transferring energy across a solid iron core. Pretty mind-blowing. If you found this journey as fascinating as I did, definitely make sure to follow TechnoSapiens for more incredibly simple visual engineering explainers just like this one. Keep questioning how the world works, and I'll catch you in the next explainer.